Okay, hello everyone in a new video. In this one we are going to solve an exercise related to radioactivity and nuclear reactions in the chapters of radioactivity and simulated nuclear reactions, fission and fusion. This exercise was a previous one in the terminal LH and SE exams in 2021 first session. Then let's start. Now exercise number 2, the title of this exercise is uranium-235. Now, the uranium atom is the heaviest atom present in the natural environment. All isotopes of uranium are radioactive. Now, number 1. Now, the two main isotopes of uranium are given by these. Now, the nucleides 1.1. Now, the nucleides uranium-238 and uranium-235 are isotopes. Why? So by isotopes, it means that they have the same atomic number, which is 92, but at the same time the mass number is different. So this is given by 238 and this is given by 235. Then let's justify, since both nucleides let me say possesses the same atomic number and this atomic number is given by 92. And at the same time the mass number is different, so this is given by 238 and this is given by 235. And this is because 238 is different than 235. For this reason, then the nucleides are considered to be isotopes. Now in 1.2 they are telling us to indicate the composition of the uranium-235, and by the composition it means the number of protons and the number of neutrons, and this can be determined by referring to A and Z. So we know that Z for the lighter particle, which is given by, or the lighter nucleus compared to 238, so Z, which is 92, represents the number of protons, and this is equal to 92. Now regarding A, so A is the mass number, which means the number that represents the mass and which is equal to the number of nucleons, and this is given by number of neutrons and protons. Or let me say the following: instead of starting by A, let me start by N. So we know that in this case, since we need to determine the number of neutrons, which is N, let me say that N represents the number of neutrons, and we know that A is given by Z plus N. Then eventually in this case N is given by A minus Z, so we can safely write that this is equal to A minus Z. And we know that the value of A is given by, in this case, 235, whereas Z is given by 92, and this is equal to 143, which represents the number of neutrons. Now, in number 2 of this exercise, they are telling us that uranium-235 naturally decays into thorium-231 by emitting an alpha particle according to the following nuclear decay. Then the nuclear decay is given. Now, in 2.1, they are telling us indicate the name and the symbol of the emitted particle alpha. So this is 2.1. Then let's start by the name. We know that the alpha particle is the helium nucleus, then let me write down. Whereas the symbol of this particle, so the symbol of this particle is important because it allows us to complete this decay. This is given by He42. Now in 2.2, indeed they are telling us to calculate Z, indicating the used law. Then first of all, let's replace this helium nucleus, or let me make some space above. Then here in this case we are in part 2.2. So before determining Z, the atomic number of thorium, let's first replace alpha by its symbol. Then here we have that uranium-235 92 decays into thorium-231Z plus the alpha particle, which is given by He42. Now in this case we need to determine the value of Z. So in any decay, the lower number, which represents the atomic number, must be conserved. Then let's say according to law of conservation of atomic number, so in this case we have that initially 92 must be equal to Z plus 2. Then what's the type of this equation? This is a linear equation in Z. Then Z in this case must be given by 92 minus 2, which is equal to 90. Then in this case the new symbol of thorium is given by TH 231, and this is 90. So let me make this as 1 to be clear, because also the upper number, which represents the mass number, must be conserved. Now they are telling us in 2.3 that the disintegration of U-235 is sometimes accompanied with the emission of gamma radiation. Indicate the cause of the emission of the gamma radiation. We know that in some of the cases, now the emitted particle or the daughter nucleus, which is given by thorium, exists in an excited state, and whenever it undergoes a transition, then this will be accompanied by the emission of a gamma radiation. Then let me say the following in 2.3. Gamma radiation is emitted due to the downward transition and this is known as the de-excitation of the daughter nucleus. Now we have reached number 3. Now they are telling us that uranium-235 is also a fissile nucleus because it may undergo fission reaction under the impact of a thermal neutron. Then according to this reaction, this is the thermal neutron and this is the uranium-235. One of the uranium-235 nuclear fission reaction is the following. So notice that here we have the uranium. So under this thermal neutron, it decays into the following. Then now if you look just at the numbers, then here we have 235, which is relatively greater than 94 on 139, and for sure 1, which means that this is the case when I have a nucleus is divided into lighter nuclei. Now in the following table they give us the masses in the atomic unit U of the following nuclei, and they gave us the value of 1 U in the SI and the speed of light in vacuum. In 3.1 they are asking us to define nuclear fission. Then, as I have mentioned, I say that this is the nuclear fission. This is the case. I have nucleus. So this is the nucleus. Why U 35 is considered to be heavy? Because this number is much larger than 94 on 139, and 1 is divided into lighter nuclei. Now let me also mention the following. In this exercise we have two types of decays, this one and this one. What's the difference between both? The first one is spontaneous because you can notice that this happens alone, whereas the other one is provoked, so it needs an intervention. So this is it's not divided alone. So, due to the thermal neutron which is here, then let me say into a lighter nuclei under the impact of a slow neutron or thermal neutron. Then this is it for 3.1, just a definition. Now in 3.2 they are telling us show that the mass defect due to this reaction is given by that. Now we know that the formula of the mass defect, which is defined by delta M to be mass before minus mass after. So mass before represent the mass of the nuclei and the particles before the decay, which are these. Then let me say it's given by the mass of uranium 235-92 plus the mass of a single neutron minus the mass after the decay has happened and given by these. So let me say that the mass of the following plus the mass of the xenon nucleus Now here we should be careful because we have 3 neutrons and we should multiply this mass by 3. And now all of these masses are eventually given in the table. Then let's start. So here we have the mass before minus open bracket all of these. Now let's start by the mass of uranium, which is given by this number. Then here we should be very careful and include all the decimal values. Any rounding must be forbidden. Now the mass of given by that. Now the mass of this nucleus. plus the mass of the plus 3 multiplied by the mass of the electron, which is given by that. Now indeed, plugging this complicated algebraic expression on the calculator and making sure that we include all the decimal, and the value of delta m is given by 0.1931, since all of these masses are in this unit U, so which is atomic unit. Now finally, in the last part of this exercise, they are asking us to determine in joules, so this is important, the energy liberated by the fission of one nucleus of uranium. So this delta m represents the mass defect due to the fission of one nucleus of uranium. So actually we need to determine the energy liberated due to this mass, and this can be done using the mass energy equivalence. So your formula, which is given by E, is equal to delta mc square. But before doing so, let's convert the given mass delta m to the SI. Then we know that delta m is given to be 0.1931 U, and we know that each atomic mass unit is given by that. Now plugging this on the calculator, one can find that delta m is given by 3.2054 times 10 to the power minus 27, and now the mass is given in kilograms. And now one can determine the liberated energy using the mass energy equivalence. So we remember, always in physics we always start by writing the proper formula, and this is given by E liberated, which is given by delta mc squared. Now the value of delta m is given by that. And C represents the speed of light. So 3 times 10 to the power 8. This is to the power 9. Expression on the calculator. Now the mass is in kilograms and the speed in the SI, which is given by meter per second. Then the value of the liberated energy is 0.8848 times 10 to the power minus 11. Since everything is expressed in the SI, we know that the SI unit of energy is joules. Then that's it for me in this video, guys. See you soon and a new one.